For the force?
No, for the
Extension. Okay. So 0.10 meters. And what was your force?
4.
4 newtons. Okay.
And then 5 newtons.
Okay.
0.14.
0 point, sorry.
14.
0.14. Okay.
And then 5.2 newtons.
5.2 newtons.
0.16.
0.16 meters. And this is extension, not total length, right?
No, I did, yeah.
Yeah, it is. Yes, it is extension.
7.
Okay, okay. Keep going.
6.
6 newtons.
0.18.
0.18 meters.
7. 0.20.
0.20 meters.
And 7.2. 0.21.
Okay, so if we graph this data, and again, if you didn't look at this until last night and forgot, we were going to do this, but Mr. Morrison didn't share the masses. So this column we totally ignore it. So if you graphed it, that's not going to be super useful to you. This one we just used, that's why we used the Newton scales to give us a relationship between the extension of the elastic and the force required to pull these things down. I mean, we could convert these things back to masses, which we're going to have to do here at the end on number 4. But for the sake of the lab, we didn't start here. We started here. So let's graph this thing. We've got all sorts of, we've got way more graph than we need for the data Naya is giving us here. So, Naya, how did you do it? What was your scale? Sorry, did I swap between Naya and Naya? I'm sorry, Naya. Keep going. What was the scale you used?
I went up by 2 for the force.
So this was 1, 2, 3, 4, 5, 6, 7, 8. Okay?
And then I went by 5, 0.5 for the bottom.
Every one of these is 0.5?
I did for the first one at 0.05.
Okay. 0.05.
No, every 5.
Okay, so 0.01 for each one of these things. Okay. 1, 2, 3, 4, 5, 0.05. 1, 2, 3, 4, 5. 0.10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's going to be 0.20. Cool. So now if we graph your data, we're going to get 0.10 and 4. We're going to get 0.14 and 5. We're going to get 0.16 and 5.2, which is going to be like there. We're going to get 0.18 and 6. Wow, this is good looking data. 0.2 and 7. This is very pretty data. And 0.21 and 7.2. So things getting a little squirrely there at the end. But not really. We're good. Let's zoom this thing in so you can see a little better. So those are her data points. I'm going to grab a ruler. If you didn't have a ruler at home, you didn't need a ruler. You just need something straight. Do we include the 0.00 on this graph?
Yes.
Why? Yeah, because for no force applied, there should be no extension, right? Okay, good. So this one is certainly one that we could include. So if you had, oh, interesting though. It doesn't quite take us back to nothing. If I just go with the data that we've been given, that might be a line of best fit we could use. So we want the slope of this thing. Slope is what? Formula for slope is? No, it's radically different. But that's okay. So, I mean, it's rise over run, right? Rise over run. So you need 2 points that actually connect with the graph. So I'm going to use that guy there, and I'm going to use that guy there. So This is a rise, so that's 4.5 to 6, so that's a rise of 1.5. And this is a run from 0.12 to 0.17. Okay, so that's 0.05. So then my rise over my run, it's going to be 1.5, and the units on this rise are what? Newtons, thank you. And the run is in meters. 0.05 meters. So I'm going to get a slope here of 1.5 divided by 0.05. Naya, what did you get for your value? What do you mean a totally different thing?
You know how you just made the line of best fit, like, just with those dots?
Yeah.
We actually connected it to 0. That's
Okay,
why
so
it's
yours,
the way.
so yours is skewed a little bit differently. Okay, so that doesn't change my question though, Jasmine. What did you get?
33.7.
Okay, so not that different than what I'm getting here. If you're getting 600, that's going to be problematic. For those of you who completed it, did you get around 30? 33? What'd you get? Yes, things got squirrely for you. Okay. Yeah, I mean, these elastics were all from same box. They're the same strength. They should all be right around the same spring constant, which is what we found here. The slope on this line, measured in newtons per meter, represents spring constant. Because we know that F equals kx, and this is the same format to y equals mx, and in this case plus b, except on ours the plus b is the y-intercept, plus b is going to be 0. So there should be no y-intercept for the reason we said before. No extension, no force, no extension. So if you included that point, yours is going to skew a little differently than mine. That's totally okay. Why wouldn't the y? It should be. But my line of best fit doesn't go through 0, 0. So no, you know that's supposed to be a point. No, yeah, it's. I mean, if you include that as a data point, that's great. Then that should skew your line of best fit down. If I extend this, it's going to bring me to 1. I'll go through 1 Newton basically, exactly there. Based on the line of best, because the data looks really good with the line that I've drawn, the data you gave me and the line that I drew. That would be where, if this was the university, like the first year labs that some of you may go into, that's where we would talk about error. Error in measurement, error in, was the rest length the same every time, or did you accidentally distort your band by pulling too hard on it? Because we talked about that too. Like, you guys all understand what it's like to destroy a slinky where it won't slink back. You can do the same thing with these rubber bands, and I think Naya and Gurkirat had that problem, where every time you relax the rubber band, it was a little bit longer than it was previously. So the y-intercept should be 0. Why? Well, because no force, no extension. And then how much should the elastic band stretch if you hung a 1 kilogram mass from it? So we can work our way. I mean, we can use the result we had here, F equals kx, and I know my k value is 30. Basically exactly 30. A 1 kilogram mass, how do we figure out the force a 1 kilogram mass exerts? Times by 9.8, good. So this is just going to be mg equals x, so that's going to be 1 kilogram times 9.8 equals 30x, divide by 30, divide by 30. X is going to equal, it's going to be just bigger than 0.3 repeating. 9.8 divided by 30. I got 0. 3, 2, 6 repeating. So almost a third. Yeah, go for it. So, I mean, we could see that too. The other way you could do that is I could have extended my line of best fit, especially given the scale that Nea gave me. It would have worked really well because 1 kilogram, wow, where did my blue pen go? 1 kilogram is how many newtons? 9.8. So there's going to be 9, there's going to be 10, and this value right here is where this thing would connect. 1, 2, 3, 4, 5, 6, 7, 8, 9. This would be 0.30, and I know I'm going to be just off the graph here. So we can see that, I mean, we calculated it, but the line of best fit also gives it to us. Because 1 kilogram is 9.8 newtons, I go over to 9.8, I go over, I go down. I would land over here at 0.32 meters. It's pretty good. So this is what I was hoping you would work through. If you struggle with this, let me know. I'm happy to assist you. But I will definitely be giving you something like this at some point in the future to analyze the data, find the spring constant of something like this. And I know I told you guys on Thursday that I was looking for a lab for us to do about egg bungee jumping. We are going to do an egg bungee jumping lab, but we have to do it after our energy unit because springs are going to come back when we talk about energy. Not yet. You don't know enough yet to do it fully. So that's that. Any further questions on this lab? That is the procedure you are supposed to go through. Oh, question 4? Sorry, is that hard to see? Yeah. So, I mean, this is how I did it using the data that Nea provided. Your data would give you slightly different values here. Yeah. And so that's how you would answer those questions there at the bottom. No worries. If you didn't get this done, you are still on the hook for knowing how to do this. And I'm happy to assist you. The other thing I wanted you guys to do were to take a look at these 4 questions. I would happily explain 4B. Let's take a look at 4B. Okay, 4B says, let's get a color that Luis can see at the back. When in doubt, black. Okay, so Jasmine, this is you? Okay. A spring is hung vertically and has a rest length of 6 centimeters. When a 1 kilogram mass is hung from the end, the spring stretches to a length of 11 centimeters. What is the spring constant of this spring? So, sorry? What will the length of the spring be if we put a 0.7 kilogram mass on it? Oh, that is actually the... Okay, let's carry on this. So what was your result then from A? What did you get? 196 newtons per meter? Okay. So now we're just going to use that in our F equals kx equation like we did for question 4. Okay. So the force then is going to be equal and opposite to the force of gravity because that's what's pulling down on this thing, right? So you're going to want mg equals kx. So your mass in this case is 0.7 kilograms. G is going to be 9.8. Your K value said was 196. And there's X. So divide by 196, divide by 196. Yo, I know. We'll get there. Because I know exactly what you did. What did you get for X? What does X represent, Jasmine? No, that is not what X represents. X is the extension. So how long was the elastic to start? So you take your extension. Yeah, length is going to equal the rest plus the extension. So the rest was 6 centimeters, which is 0.06 meters, plus the 0.035 meters you get. So the total length is going to be 0.095 meters, which, if I'm not mistaken, is 9.5 centimeters. which is the value we're looking for. That the tricky part there is remembering what these values actually represent. X is not the length of the stretched spring, it is the extension. How far have you pulled it from where it was before? So you have to go back and add that original 6 centimeters in there. Thank you for asking the question. I'm willing to bet you weren't the only one. Anybody else? Okay. Oh yeah, I did not forget, but thank you for reminding me. I actually started recording after we had put the scale down, but before I'd done anything else. Oh, did I forget to put it up again?
2 days ago.
Email me. If the video's not there, please let me know.
Okay.
I will put it up. I can do that from anywhere. If I forget, God let me know before class. I'm sorry that I forget, but God let me know. If you're looking for it and can't find it, please say something.
I remember about the graphing that we did with, I don't remember having to do this adapted worksheet, because I was looking at the video and then...
Yeah. Okay. Now for something entirely different. Flip the page again. Here we go. This chapter now is just you've kind of figured it out at this point, but we're going to start jumping from one kind of force to another kind of force to another kind of force, and then analyzing how these different forces behave. So we've done gravity, we've done friction, now we've done spring constant, or spring force rather. Now we're going to do tension. Now tension's a lot easier than these other things because tension doesn't have its own formula to it. Tension is just tension. It's the behavior of cables or strings or rope or anything that isn't solid.
Is it straight line?
And we will deal with them as far as they're concerned in straight lines, yes. So tension occurs within a material when that material is being pulled on. Again, just like we've talked about before, like everything has a spring constant, just some spring constants are going to be really short because not everything stretches to the same degree. Any material can theoretically have tension, but when we talk about tension, we're going to talk about objects that we are most used to seeing deal with tension. Things like cables, things like ropes. So tension is an internal force that acts at all points equally and oppositely along a rope, a string, or a chain, a cable, whatever, in both directions. Oh, that's really hard to see, I'm sorry. Hence the term equal and opposite, right? Like they're going both ways. Because the rope itself isn't moving at every single little chunk. You're pulling on one end, the object's moving at the other end, and the rope connects the two. So we're going to consider two carts attached by a rope being pulled along a flat surface. These things have wheels, so they're rolling, and because they're rolling, we're going to assume that the axles are perfect, so we can ignore friction. Otherwise, this makes it a lot more convoluted. If mass 1 is pulled to the right by a force of 40 newtons, what's the acceleration in the cart? So let's talk this through. There's a procedure for going through a system now with multiple objects. We want to free body diagram this thing. What forces are acting on our system?
You have like the gravity and the normal ones that are equal in space.
Okay, so I've got gravity and I've got a normal force. So these things are on the ground. And I heard an FA. So I've got FG acting down. I've got FN acting up. FG down, FN up. What are the values there? Does it matter?
I don't think so.
Well, give us the values for FG. 6 times 9.8 and 4 times 9.8.
equal to 40 million.
This is going to be 39.2. Okay, and now we've got an FA acting to the right. And Luis, you just said that was 40 newtons. Oh, sorry. What other forces are acting on these two objects? The tension, so the rope. How do we draw that on here? So this guy's being pulled by what force? This guy's being pulled by the rope. So tension has to be pulling this way. But if tension is pulling to the right here, what has to be happening to this right here? It's going to the left. And because this is the same rope everywhere along the rope, what do you know about these two tensions? Gotta be equal. So I can call, I don't know what it is, but I can call it T in both cases using the same variable because it's the same tension. If I had multiple ropes, I'd have to label them T1, T2, T3 for as many ropes as I have. But for this one, there's one rope, there's only one tension. So now we're going to figure out the acceleration of the cart. This chapter is dynamics, and for everything in dynamics, we start where? F net equals ma. Okay, so yeah, we're going to treat this thing acting as one large system. So what are the forces acting on this entire system? There's O, and that's the other thing we haven't done. What am I missing? There's no friction. There's one more thing we want to add to the diagram to make sure we stay consistent. Which way do we want to be positive? Naya, which way? That would be the one that makes the most sense, but we should make sure we explicitly put that in there. So that way is going to be positive. So let's take a look here. I've got my F net equals ma. What forces are acting in the plane of motion or in the direction of motion for our system? Hold on, Luis. My bad. I did when we originally talked about tension. I said I was going to call it FT because big T was something else. Thank you for reminding me, Luis. So I've got FA and I've got two different FTs. So what's my F net equation going to look like over here? FA plus FT minus FT. Because, what does that just mean? Well, and in opposite directions. This FT is in the same direction as our positive, what we call positive. This one's in the other direction.
Why do we even write FT then? Because that would cancel out.
I'm writing it because I want to make sure everyone understands explicitly that it cancels out.
It's like normal force and gravity. They cancel each other, but we still write.
Kind of, except these ones are acting in the plane, so we have to at least acknowledge that they exist and why we can eliminate them. So we're going to have FA plus FT minus FT, and that's going to equal the mass of our system, 6 plus 4, because the whole thing is accelerating, times A. Well, FA was 40. These two cancel. Is going to equal 10A. So then what's the acceleration of my object? For what? No. There you go. Meters per second squared. Okay. Note here, you said it already. I'm going to write it down again. Tension cancels out.
Does it always cancel out?
Because it's equal and opposite. Almost always.
Okay.
When you're finding the acceleration, yes, it cancels out because we deal with this thing acting as a system. Now, if I wanted to go find that tension, I want to figure out what Ft is. We're going to isolate one block. Okay, so I'm going to go back up here. When we're talking about the acceleration of the carts, and you know what, and I'll call them carts down here. We deal with them, or deal with both. Because they accelerate together, we deal with both together. When we want to find the tension between them, we isolate one cart. Now, we've got our free body diagrams already. Pick a cart, I don't care. Okay. Left. Why left? Okay, because you read left to right in this country. Sure. So let's pick the left. Left is actually the better option. So you guys have chosen the left cart. For the left cart, what is, or what are rather, the forces acting in the direction of motion?
Gravity, normal,
In the direction of motion, Connor.
tension.
Tension is the only one. The only thing that's causing this cart to accelerate is this force right here. So in our dynamic equation, we're going to have force of tension is going to equal, now the mass of just this cart is 6, and we know that this thing accelerates as a system, and we found the acceleration to be 4. So then what is the tension between those two blocks, or those two carts? Sorry? It's going to be 24 newtons. What if instead we had isolated the right cart? It's a little bit more work. Let's show it though, just so we can see it. F net equals ma. Now if I had isolated the right cart instead, what forces are acting in the direction of motion on the right cart? Applied force and tension, and which one of those is positive? Fa. So for this one, it's going to be Fa minus Ft equals ma. Fa was 40 minus Ft equals 4 times 4. Sorry, I'm running out of space here. So I'm going to get 40 minus Ft equals 16. How do I solve for Ft? So you want to add, I'm hearing Jasmine's committing to this, adding Ft to both sides and subtracting 16 on both sides. Here that's going to cancel, so that's going to give me 40 minus 16 equals Ft, which is 24. I mean, we better get the same value because tension has to be the same everywhere in a single rope, and we did. How come this one didn't show up as negative? What happened there? Where did the negative get dealt with here, Tenjo? Yeah, because I made it explicitly negative here, this value is going to show up positive because here is where I said, well, Ft is going to be negative, and then the value is 24. That's why this final value isn't negative, even though it's pointing to the left. Okay. Questions, comments, concerns? Relatively straightforward, yes? Okay. Since it cancels out of the total F net equation, we only consider the forces acting on one mass, which is why I isolated one or the other, or one cart. And since tension acts on both masses equally, we can use either one. What about friction? Because why wouldn't we bring friction into this?
Well, because it's just another thing.
Let's imagine that the wheels fall off of cart number 2 and it drags along the ground with a coefficient of friction of 0.32. What happens to the tension? What do you think is going to happen to the tension?
Going to be more tension because the tension that is going to the left direction is going to increase, and that's going to make the acceleration to decrease. And in the formula, F net equals ma, you need to put
Oh, okay, hold on. Before you go any further, I like what you've set up to this point. It was good, but we're going to show it. We're going to draw it out first, and then I'll come back to you, Luis. Yeah, Manuel.
I'm thinking of it, if it slows down, the acceleration is also decreasing, which would make them come a little bit closer. Wouldn't that make the tension less as well? If I'm thinking of that correctly.
They're not going to come closer because the wheels are falling off this cart. This is M2.
Oh, I thought that was right.
The wheels are falling off the back one.
Right.
So then it immediately starts to drag more. I understand what you mean. You thought they came off this one, so then this one keeps rolling forward, decreasing tension. If this were M2, that would be correct. Connor.
Well, if the applied force, if the thing that's moving them keeps moving them and the acceleration never changes, they never slow down.
We don't know if the acceleration is going to change or not.
Exactly. So if they keep working harder, it's going to put even more tension because there'll be way more friction. Will be much heavier on the when it's dragging on the ground. I don't know.
Well, it was 0, and now there's friction, so yes, it's going to be bigger.
Yes, but anyhow, it's going to create more force in the in the velocity forward. To keep it
Now,
Ah.
Connor, you're doing that thing that you do where you start making things more convoluted than they need to be. Luis, you're going to take this over. Let's draw it. Here we go. Let's prove whether or not Luis is correct. Now, the situation has slightly changed. I still have cart number 1 on wheels. But now I have cart number 2. The wheels have fallen off, literally. And this guy's sitting on the ground. So now all of a sudden, what is really important to include on these free body diagrams? Well, friction, but even before then, well, what did we say? Oh, before we don't need those values, but now we need them. No. Yes, thank you. We now, because these wheels are now gone, this thing is going to be sliding. We absolutely have to include Fg and Fn, because that's going to give us our value for friction, right? What's the formula for the force of friction? No, what is the formula for the force of friction? General formula for the force of friction. The coefficient times, Khalil, keep going. The coefficient times the normal force. So we need the normal force, which means we need Fg. Here we go. So free body diagram, we found the values already. Look at us go. Fg equals 58.8. Why are Fn and Fg equal and opposite? Why are they balanced? It's not going up and it's not going down. That's one reason. The other reason is the ground here is level, so Fn is perpendicular to it, which means it's opposite Fg. Remember what normal force actually means. So Fn is going to equal 58.8. And I've got a force of tension acting that way. On this guy, I've got a force of tension acting this way. I have an Fg down of 39.2. I've got an Fn up. We don't need these ones, but we'll include them anyway, because a free body diagram should include all your forces. And we still have that applied force of 40 newtons. These should all be newtons. Okay. Oh, one more force, because this thing is rolling. Not rolling. It's no longer rolling. It's dragging along the ground with a coefficient of friction. Which way is friction going to act? Opposite the applied force, because it's going to oppose motion. Good. So force of friction acts on this block to the left. Force of friction equals, and we'll put it in here already, mu Fn. That Khalil gave us earlier. And we can figure it out right away too. The coefficient of friction is 0.32. And the, oh, that should be Fn, not just n. And Fn is 58.8. So what is my force of friction on that block? 18.816. Jasmine, you have the same value? Okay. So now we're going to go through the same equations that we did before, or same calculations we did before. Because to figure out tension, we need to figure out what the acceleration is. So now I've got, oh, and which direction do we want positive to be? To the right. Okay, let's do it. We start with F net equals ma. And this is for the entire system. So what forces are acting in the plane of motion? Which ones of those are positive, Luis, and which ones are negative?
One F2 is negative and FF is negative.
Okay.
F is positive and FA is positive.
So it's going to be FA plus FT, these two that are acting to the right, minus FT, acting to the left, minus force of friction, also acting to the left. Good. And that's going to equal the masses we had before is still 6 plus 4 times our acceleration that we're looking for here. So FA is 40. That guy and that guy are going to cancel out. Minus 18.816 equals 10A. What's the value for the acceleration this time? So 2.1 something? 2.1184 meters per second squared. So we found the acceleration. Now to find the tension, we focus our attention on one block. Which block do you guys want to use? Left one again? Okay. So then what's my F net equation going to be for the left block? Sorry? So if we look at just the left block, Ft is acting in the positive direction, minus Ff, good. Ft minus Ff equals, and now we want just the mass of the left block, so that's going to be 6. And we know the acceleration on the block is 2.1184 because it accelerates as, as a system. So Ft is what we're looking for. We know that's 18.816 equals, what's MA? No, I just want the 6 times 2.1184. 12.7104. And I'm going to add 18.816 over to both sides. So I'm going to get Ft, yes, Luis, you're right, 30 point something, 30.5264. 31. Right, yeah. 0.5264 newtons. So was he right? What happened to the value for tension? It increased. So your intuition was correct, which is good. It's nice. Isn't it nice when intuition and math agree? Not like everything else that we did earlier when the intuition and math totally disagreed. Okay, let's make the tension more interesting. Okay, so hands up if you've ever played with a pulley. Where?
This is my grandpa's barn.
Oh, like big, or like lifting engines kind of pulleys. Nice. What's the purpose of a pulley? Does anyone know?
Just to make lifting stuff easier. So there's a lot, like instead of lifting stuff like an engine, like as you mentioned, it's a lot heavier. And I can't remember exactly what it is, but it just makes it a lot easier to lift. It makes it lighter.
Offsets the mass.
Effectively, yeah. So what pulleys are for, and the simplest terms, the purpose of a pulley is to redirect forces. Because if I act in a particular way on this guy, if I pull down on this block, what's this block going to do? It's going to go up. Why? Well, because the pulley is allowing me to redirect the force that I'm applying here. A downward force here is going to cause this block to go up. Yes?
I was using a science museum, Sao Paulo, and the thing that I learned about it, I think that this thing divided the amount of force that you needed in parts of the engine. So the force that you need to apply to lift the thing is lower because it's not only you that is applying force, the engine, the like big ball there is to making force in the thing, so it's easier to lift it.
Yeah, so whole systems of pulleys, yes, do what you're describing. When we only deal with one pulley, which is what we're going to end up dealing with here, it doesn't have the same effect. So what you're used to seeing is a contraption made of pulleys that allows you to do something a lot easier. A simple pulley is one. Well, it's just a single pulley. We're going to drape the rope over it, and we're going to hang up two masses from it. A simple pulley, just all it's doing is allowing us to redirect. So the reason I ask you about your experience with pulleys is because I want to, yet again, we're going to compare your experience with it with what the math is going to show us here. So you got to understand there's two different pieces here. Your experience with pulleys is a full-on contraption, rather complex contraption, made of pulleys, and that is designed to reduce the amount of force necessary to lift something real heavy. Simple pulleys, all they are designed to do is redirect forces. Yes, you can combine them to do all sorts of cool stuff, but for the sake of what we're doing, I need you to put the contraption aside and focus just on the one. The other thing that we're going to do here, one of the things that you don't do in real life, but that we are going to do here, we are going to ignore two things. We are going to ignore the mass of the rope. Because as soon as you don't ignore the mass of the rope, it brings in mathematics you guys don't know yet. And for the first time, I actually did it for the first time as part of my master's, and it's way more complicated than even I thought. So we're going to ignore the mass of the rope and friction in the pulley. For all of these questions, we're going to assume that the rope has no mass and that the pulley has no friction. Both of those aren't true, but for the sake of what we're doing, we're going to assume that it is. What this system allows us to do is, as I said before, it's allowing us to redirect the forces. Now, to analyze these things, what we can actually do is just unfold them off of the, yes, Niraj, you may use the washroom. Because you guys always ask right around this time if that's something you can do. You just had that look in your eye.
Oh my gosh.
It's actually what I assumed you were asking before, Manuel, when I was nodding and then you didn't move, so I knew you weren't trying to go to the bathroom.
That's getting scary.
I'm getting to know you guys. You know, it's been a couple months. It's been a couple months. So because the pulley is just redirecting the force, we can redraw this as if the pulley isn't there. Okay? This thing, I wrote it in here as being unfolded, but basically what you're doing is you're picking this object up off the pulley and stretching it out like this. So this thing turns into a system that looks like one we're used to seeing. For the sake of this, I'm going to label the left mass M1 and I'm going to label the right mass M2 so that I can call this guy M1 and this guy M2. Now, what forces are acting on M2? There's gravity. In this diagram, gravity is going which way? Straight down. And I'm going to call that Fg2. What else is acting on this block? Does it say anywhere that there's an applied force?
I don't know what to call it, because technically it's the reverse force from gravity, tension pulling it back.
Okay, so there's tension pulling it back, you say. Excellent, love that. I'm going to call this Ft2 just because they're both on block number 2. What forces are acting on block number 1? Fg1, also straight down. And upwards I'm going to have what? Ft1. Are there any other forces acting in these two blocks? Someone just needs to say the word. Are these resting on any surfaces? Well, do you see a surface? I mean, the whole purpose of the pulley is that they're hanging there. So no, there is no normal force.
Maybe the slight spring?
We are going to ignore springs in ropes because the spring constant of a rope is it's basically non-existent.
Well, that's the only thing I can think of.
I mean, the answer could be no. Khalil.
What was the middle thing on top?
This thing here?
The weight from the two blocks is pulling down on it. Oh.
Yeah, there's gravity.
Yes, if we want to include the forces on the pulley, we could acknowledge that as well. There's going to be a force. Well, there's going to be a pull down on here, but the pull down on this is just going to be the sum of these two. So we've got all the forces acting on this system. We've got gravity acting on the two blocks. That's going to be the downwards here. Did we throwing stuff over there? Actually, no.
Bruh, I'm literally coming out.
He snuck in right before the 10:10 roll.
It's 10:10?
Oh yeah, there's like only 10 minutes left.
What?
Let me finish this example, Manuel. Okay, fine. If you're going to die, Manuel, you can go. If you're not going to die, then stay. I'll let that, your judgment. Okay, so,
No, yo, I'm out of here.
guys, bringing it back together, there is no forces acting on here. I let him choose whether or not this was a good time for him to go. So I'm just because the same way I picked this up off a pulley, stretched it out and dropped it down here, I can do the same thing here with the way I've drawn these forces. So mass 2, which way is this force going to be pointing for this object? To the right. Good. And I'm going to have an Ft2 pointing to the left. What's pointing to the right on this block? And to the left on this block? Fg1. What do we know about Ft1 and Ft2? Thank you. These two have to be equal. And now from here we can go through setting this whole thing up. Let's do that. Yes. You betcha, Khalil. Okay, here we go. Two masses. And this will be the last thing we do. I know I'm pushing you guys right to the bell. This will be the last thing we do. I've got two masses shown hanging from a frictionless pulley, and they're released from rest. We want to find the acceleration of the system and the tension in the spring. So this is what we've got. Sorry, string, not spring. Guys, hang in there. Connor, that doesn't help. Let me control my class, or attempt to control my class. Luis, what forces are acting on my blocks?
Gravity, tension in the two ropes.
It's the same rope.
Yeah.
So I just have to write FT once. Perfect. What's FG here for the 6 kilogram block?
FG is gravity times 6, I don't know my hat, is
58.8.
Okay, so that's going to be, thank you, Zaid. 58.8 newtons. What's the force of gravity here?
199.8.
Which is?
I don't know.
Same value from the last question, 39.2. So now to figure out the acceleration of this system, we take the system off the pulley, we lay it out flat, and we're going to get a system looks like this. Where I've got FG going that way. That FG is the 39.2 because that's the 4 kilogram block. This is the 6 kilogram block. I'm going to have FG going to the left, 58.8. I'm going to have an FT in and an FT in. Which way are we going to call positive?
Well, it's actually to left, yeah.
To the left makes more sense in this case. Why?
Because it has a greater mass.
Because that's the greater force, yeah. If I said to the left on this diagram, what is that going to look like on this diagram? Sorry, Tristan? Like up and over this thing. Absolutely. I love it. So the direction that is positive, I'm going to put it on the pulley as well. It's up and over this way. Why? Because when these things release, it's going to go like this. And so we want up to be positive here and down to be positive here. Pulleys just redirect it the same way they redirect a rope. So then to find the acceleration of the system, F net equals ma. I'm going to have Fg minus Ft plus Ft minus the other Fg equals the mass of the system, because the system accelerates together. So this Fg is the 58.8. These guys cancel. Minus 39.2 equals 10a. What's the acceleration? You said 11.96?
I got
1.96. And then to find the tension in the string before the bell goes in less than a minute, we focus on one block here. Which block do we want to use? Jasmine, pick a block. Left block. So then what's my F net equation going to look like? Angelina? What's my, if Jasmine picked this block, what's my F net equation going to look like? Is it going to be Ft minus Fg or Fg minus Ft? Yes. It's going to be Fg minus Ft equals ma. Fg for this block is 58.8 minus Ft, which is what we're looking for, is going to equal the mass of that block times 1.96. And I'll finish that tomorrow. You have no homework. We spent too much time going over the homework we didn't all do from Thursday.